In this video, we're going to talk about conservation of energy, and that's an idea we've already talked about a little bit. If all of the forces involved are conservative forces, and conservative forces include gravitational forces, it includes elastic forces for ideal springs. Later we'll learn that it also includes things like electromagnetic forces. But today, I think in this chapter, our conservative forces will pretty much be limited to either gravitational forces or elastic forces. Non-conservative forces do not conserve mechanical energy. They cause energy losses. The non-conservative forces we normally deal with are things like friction and air resistance. Both of those will convert some of that mechanical energy into thermal energy. So that's really what we want to talk about. And finally, we'll talk about what we mean by power. Now, if mechanical energy is conserved, then we have a situation where the initial kinetic energy plus the initial potential energy, and this could be gravitational, elastic, or both, will equal the final kinetic energy plus the final potential energy. So let's look at an example. Suppose we have a frictionless pulley. If it's frictionless, then I know I don't have to worry about those non-conservative forces. So essentially the only force that we're going to have in this problem is gravity. I have a pulley. There's block A, and here's block B. And they tell us that the mass of A is greater than the mass of B. Here's somebody's hand. So I'm going to draw a hand holding it. It's a terrible looking hand, but somebody's holding block A for right now. When they let go of block A, we know what's going to happen. If we wait just a minute, we'll have a situation draw this, where A will fall and B will rise. Why? Because the downward pull of gravity on A is going to be greater than the downward pull of gravity on B. The question wants to know what's true. Here are our answer choices. Gravitational potential energy increases and the kinetic energy increases. The gravitational potential energy decreases and K increases. Or the gravitational and kinetic energy are constant. Those are our choices. Well, let's stop and think. If we have a frictionless pulley and the only force acting is gravity, then we know the mechanical energy is constant. The sum of kinetic plus potential won't change. That doesn't mean individually they won't change. Right here, there's no motion. But as soon as he removes his hand, the system goes into motion. So we definitely know that kinetic energy increases. So that limits us to A or B. Conservation of energy says if the kinetic energy is increasing, then gravitational potential energy would have to decrease. So our correct answer is going to be B. Now notice A loses gravitational potential energy, B gains gravitational potential energy if they were both roughly here to begin with. However, A was larger. A lost more gravitational potential energy than B gained. So overall, the gravitational potential energy decreased. So kinetic energy would increase, gravitational potential energy will decrease. Happens all the time. If you put a marble at the top of a ramp and you let go, when it rolls down the ramp, the kinetic energy is increasing while the gravitational potential energy is decreasing. So another example. This example reminds me a bit of your lab of gravitational potential energy. In this we have Rocky and his skateboard, and they have a combined mass of 25 kilograms. So this is a kid, it's like 60 pounds. If Rocky starts at the rest from the top of a frictionless quarter pipe just means it's a quarter of a circle. So here's the ground, there's the top, there's the bottom, and then there'd be the rest of the ground. So this has no friction. He's up here on his skateboard. There he is, ready to skate. The quarter pipe, it says, trying to draw this pretty accurately, has a radius of r. It says, if Rocky starts at rest from the top of a frictionless quarter pipe, derive an expression for his speed at the bottom of the ramp. We want to know his speed at the bottom. And it's important, it says he starts from rest. Well, this is initial when he's at the top. When he reaches this point down here at the bottom, there's his skateboard, there's Rocky, still on his feet. That's going to be your final. Well, at the very top, his initial kinetic energy is 0 because he starts from rest. His gravitational potential energy is given by the formula mgh. But how high is h? Well, if this is a circular quarter pipe, then that distance is r, just like this distance is r, all of those distances. So it's mgr. When he reaches the bottom, we know he's going to be moving, so he'll have a final kinetic energy that's 1/2 mv squared. However, his height above the ground now is 0, so his potential energy has fallen to 0. So this is pretty classic conservation of energy. He started out with a certain amount of potential energy, all of it got converted to kinetic energy. So if we want to solve for V, we notice the m's cancel. We end up getting V squared equals 2gr, and therefore V is simply the square root of 2gr. They later come back and say, okay, well, if r is 3 meters, how fast will he be going? Notice it didn't depend on his mass at all. So r is equal to 3 meters. His speed is the square root of 2 times 9.80 times 3. And to 3 significant digits, he'll come out going about 7.67 meters per second. Pretty classic problem. He only had potential energy at the beginning. It all got converted to kinetic. You can see how fast he's going at the bottom. Let's do something that also requires us to use elastic forces, because we know elastic forces are another type of conservative force. This one I believe is in your textbook. Also, this example is labeled something like elevator safety. And it says that we have a 2,000 kilogram elevator falling at 8 meters per second when it contacts a cushioning spring at the bottom of the elevator shaft. The spring is meant to stop the elevator by compressing 3 meters. Determine the necessary spring constant. So this is kind of a fun problem. We've got this picture. Here is the elevator shaft. And sitting in the bottom of this elevator shaft, this is its equilibrium position right there, is a spring. All right, and the spring is meant to, it says cushion it at the bottom. Now, the elevator itself weighs 2,000 kilograms. And it says at the moment that it reaches the top of the spring, the equilibrium of the spring, call this x equal, no, let's call this y equals 0 since it's vertical. It's going 8 meters per second. So at the moment that it first hits us, what's going to happen? Well, what's designed to happen, it says, is that this spring will compress a distance of 3 meters. So this distance that it compresses from here to here was 3 meters. This is our 2,000 kilogram. Okay. At this point, we know it stopped. So this right here, this is V0, it's going 8 meters per second. Right here, this is sort of our final, it's going 0 meters per second. Now, what's really interesting is this wouldn't work very well. It would come down, it would compress it, but after it reached this equilibrium point right here for a moment, it would turn around and bounce you right back up. So I'm not so sure that that's actually an ideal way. It's like a giant shock absorber down at the bottom of the elevator. Okay, they want to know the spring constant. This is classic conservation of energy. We have initial and final energies. Let's look at the initial and let's see if we can figure out how we're going to go from here. Okay. We have, I kind of think I want to change something, but we're going to have to decide. No, maybe we'll just leave it exactly the way we have it. All right, at the initial conditions, we have kinetic, 1/2 mv squared. We have gravitational potential, mgh. We have elastic potential energy, 1/2 ky squared, since I used y. Okay, we haven't put any numbers, but all of these are initial. So you could put zeros or i's. We'll use I. Change that to an I. That's final. Okay, so there's all that initial. The initial kinetic, the initial potential, this gravitational potential, the initial gravitational elastic. That has to equal what's going on at the end. That is an x, kx squared. Nope, it's a y. Okay. We did it vertically, so we use Y. So let's look at each of these things. Right here, if we let this be our equilibrium position, do we have kinetic? Absolutely, we're going 8 meters per second squared. So that's going to have numbers put in. That's going to have 1/2 2008 squared. That's our kinetic. What about MGH? Do we have gravitational potential energy here? Well, in a sense we do, but in a sense we don't. If we decide that we want y equals 0 to be right here, then this is the point that we are calling no gravitational potential energy. So actually we do not, okay? What's going to happen here is we're going to have negative gravitational potential energy. Perfectly fine. That still means we have more here at 0 than we do here with gravitational potential energy is negative. So I don't even need this. This is going to be 0 because it's at a height of 0. I'll write that down even. So that's 0 for gravitational potential energy. Do we have any elastic potential energy? Again, this is 0. If our initial position is right here, the spring is not compressed at all. I have no elastic potential energy, another 0. So we really could have written an equation that just said 1/2 mv initial squared and not even needed any of this yet. But we want to look at all 3 types. Afterwards, the velocity is 0. So my kinetic here is 0. I do have a change in potential energy. This is going to be mgh final, so 2000 9.8 times -3. So our potential energy was 0. Now it's even less. But it's important is the change in potential is the same. We would have gotten the equivalent result if we'd have said 0 was here and this is +3. We'd have had the same amount more here than here. And then finally, our spring is compressed. So that is going to be 1/2 K that is compressed 3 meters, 3 squared. We know every single thing except for that K. So actually working it out will not be terribly difficult. If I do, that's going to be 1,000 times 64. It's going to be 64,000 equals 2,000 times 9.8 times -3 is -58,800 plus 9/2. That's 4.5 K squared. Everything, I'm not K squared, K. Everything at this point is just algebra. 64,000 plus 58,800 divided by 4.5. And I get a very stiff spring constant. My math says this, but I only had 3 significant digits, so I'm going to say it is 2.73 times 10 to the 4th newtons per meter. The fun part is setting it up. Once you get the hang, pick where your equilibrium is. You have to decide on that because you're going to measure gravitational potential energy from an equilibrium position. It doesn't have to be the ground. The ground wouldn't have helped us at all. Our choices that would have worked were either here or here, because this basically was the beginning of the problem and this was the end. And either one of those would have worked for y equals 0. Okay, let's move on then and let's talk about what do we do if we have friction. How does friction or any non-conservative force change this? When we're dealing with a non-conservative force, we know that we end up with something like this. Just say we have our initial kinetic, our initial potential, plus this non-conservative work. The textbook calls this other work. Okay, remember work and energy have the same units, they're very equivalent. Generally speaking, this other work will be a negative quantity. The work done by friction is normally negative because it opposes the motion. So the force is in one direction, the displacement's in the other direction. So this is a negative quantity that's going to reduce how much mechanical energy you have. Just remember these two combined, that's your mechanical energy. So when we get done, that is going to give us the final kinetic energy plus the final potential energy. Since this is a negative quantity, this will be less. We're going to lose. Now, we know you cannot lose energy. So even though we, quote, lose mechanical energy, that energy doesn't disappear. It gets converted into a non-mechanical form, and in particular, heat. So let's do an example where we have to consider this work done by friction, this other work. So this example's in your textbook. It concerns a glider on an air track, and we've looked at this picture before. There's an air track. Here's a glider sitting on it. Maybe need to make it a little longer. It's attached to a spring. There's equilibrium. And then it's pulled out here farther. So that the spring gets stretched. And it's released. So generally, we'll call this 0. And here is some new position. I'll call that X final. So we started at 0, we pull it out some other point. It says a glider. The mass of the glider is 0.200 kilograms. And it is at rest at x equals 0. This is the beginning of the problem. It's at rest, and the spring is not stretched. So we are at the equilibrium, the natural position right here. We're not stretched at all. It says you apply a constant force of 0.610 newtons to the glider. How fast is the glider moving when it's moved to 0.10 meters? The force constant is 5 newtons per meter. And we want to know how fast it's going. All right. There's a couple of ways you can look at this problem, but essentially what you want to understand is you're a non-conservative force. When you come in and you pull this back, you're doing other work. You're the work other in this situation. So let's write we've got our conservation of energy. Our initial kinetic energy, our initial velocity is 0. So our initial kinetic energy is 0. Our spring is unstretched. We don't have any elastic, it's also 0. However, in this case, we have work done, and it's actually positive work. So this isn't actually a friction problem. This is just some outside force doing work on the system. Work is force times distance. So this other work is 0.610 newtons times, how far does it stretch it? You moved it to 0.1. Meters. And that has to equal the final kinetic, 1/2 mv squared. Mass is 0.2. We don't know v. The elastic force is 1/2 kx squared. And we do know x. All we have to do is solve that for this one unknown form. 0.610 times 0.1 is 0.0610. That's how much work you did when you pulled it from here to here. 1/2 of 0.2 is going to be 0.1 v squared. And then the energy in the spring, this final potential energy, because now that you've stretched it, we have potential energy. 1/2 5 times 0.1 squared is 0.0250. If we subtract and we solve this, we get 0.036 has to equal 0.1 v squared. 0.36 has to equal v squared. So v equals 0.600 meters per second. Okay, I want to do one more, and I really like this next problem better because it involves friction, and I think friction is what you're going to see come up more often than something like that. Let's go back to Rocky on the half pipe, part 2. Actually, it's a quarter pipe. So here's Rocky. Here's our picture. We know that this is R. And we know that R is 3 meters. Here's our little skateboarder. Our skateboarder has a mass of 25 meters. I'm sorry, 25 kilograms. Mass has to be in kilograms. All right. It says Rocky on the quarter pipe, part 2. Suppose the ramp, radius 3 meters, is not frictionless. If Rocky's speed at the bottom is only 7 meters per second, so how much work was done by friction? You could have put an F, work done by friction, work done by non-conservative, but basically it's asking the question, how much energy did you lose? So here we go. Initial plus this work from this non-conservative force has to equal final plus final. Initially, he starts at rest, so we'll even know V initial is 0. So he starts at rest. So initially this is 0. His initial potential energy, of course, is mgh. So 25 times 9.8 times 3 meters, plus this non-conservative work that's going to be done by friction. We don't know how much that is. At the bottom, we do know his final kinetic energy is 1/2 his mass times his final speed squared, and his final potential energy, since he is back down here at ground level, talking about when he's here, his final kinetic energy, his final gravitational potential energy is simply 0. So there we go. So after 25 times 9.83, he starts off with 735 joules of energy. There's our non-conservative work. His kinetic energy at the end is 613 joules. You can see he lost energy. I have to subtract. I end up getting that the non-conservative work is negative 122 joules. That's the work that was done by friction. Okay, to move on, our last topic is power. And power is another word we use a lot in everyday language, but when we're talking physics, power has a very specific meaning. Power is the rate of doing work or using energy. And of course, doing work is using energy. I'll usually tell students, if you think about it, suppose 2 students go home and they do the same 20 math problems. They both get them right. One student does 20 math problems in 30 minutes, and the other student does 20 math problems in an hour. They both accomplished the same amount of work, but the student that did it in 30 minutes would be more powerful. Her rate was twice as fast. The definition is usually written something like this. For average power, this is average power, it is simply the work divided by the time. Some people will write this as intervals, as in the change in the amount of work over a time interval. I kind of just like this. Obviously, if you want the instantaneous power, you make this time period very, very short. One of the things that we do know, and we'll look at this average power with the time intervals, is that we can rewrite this We know that work is force times distance. This is often written as it's a force times the displacement over the time interval. Work is force times the displacement. This is a time interval, but what is this quantity? A change in position or a displacement divided by a time interval is simply a velocity. So an alternate definition for power can be that it is the force times the velocity. It is important to point out that power is a scalar. And that the SI unit is the watt. 1 watt is 1 joule per second. Another familiar unit that you may know is the horsepower. 1 horsepower is 746 watts. Now, I want you to be careful because I've just introduced a unit with a W. We have this lowercase w, sometimes with an arrow, sometimes usually without. That means weight. You can tell its weight because it will have a unit of newtons. We also have this, uppercase W. That stands for work. You'll be able to tell its work because it has a unit of joules. And we have another lowercase w, which of course is watts. You can tell it's watts because it is a unit. All I'm trying to say here is be careful with the W's. Read the problem. Are they talking about weight? Are they talking about work? Are they talking about watts? If it's 15W, they're talking about watts because W is the unit, right? If it's W equals 15 newtons, they're talking about a weight. If it's W equals 15 joules, they must be talking about work. Unfortunately, an uppercase W and a lowercase w don't always look that different. All right, let's do just an example or two. The first example says a jet engine has a forward thrust of 1.50 times 10 to the 4th newtons. A forward thrust is a type of force. You can tell it's force because of its units. When the plane is traveling 300 meters per second, so we have a speed or velocity of 300 meters per second. That's about 670 miles per hour. If you want to know how fast that is, it's pretty fast. What is the horsepower? Well, before we find horsepower, let's just find power using our units. We know that power can be found for something that's in motion by doing force times the velocity. So we have 1.50 times 10 to the 4th newtons times the speed of 300 meters per second. So the power is 4.50 times 10 to the 6th watts. All I want to do is do a conversion on that. I have 4.5 times 10 to the 6th watts. I know there are 746 watts in 1 horsepower. If I do that division then to 3 significant digits, it comes out to be about 6,030 horsepower. Pretty straightforward. Let's do another example. This example, we have a marathon runner, and the marathon runner has a mass of 50 kilograms. He runs up the stairs. To the top of the Sears Tower. So we've got a 50-kilogram marathon runner running up flights of stairs. Doesn't have to be running up in a straight line. I'm sure their stairs do like stairs do. To this height of 15 meters. Okay. Oh wait, I said that wrong. I did not do that. So that's not very tall. That can't be the height of this. I'm sorry. Of 443 meters in 15.0 minutes. The question is, What is her power? Well, first of all, power is work over time. How much work do you have to do to climb stairs to get to 443 meters higher than you were? It's just force times distance. And remember, work done against gravity, that's a conservative force. It doesn't matter how you get from the bottom to the top. It only matters the change in your position. So the work done, force times distance, is just mgh. 50 kilograms times 9.8. Remember, the force needed to lift a mass, even yourself, is just your weight, times a height of 443 meters. And I did not get that figure separately. I did it all in one step. I'm going to stop. So 50 times 9.8 times 443. Ooh, it's a fun number. It's 217,070 joules of work. Power is work divided by time. But 15 minutes does need to be changed into seconds. We know that every minute is 60 seconds, so I'll just do 15 times 60 seconds. I take my previous answer and divide it by 15 to 60. It's that to be about 241 watts. Okay, that finishes up chapter 7. Thanks for watching.